So thank you everybody for joining us today. This talk on the roadmap to quick and effective asset decarbonisation will last around 20 minutes. So in terms of the agenda for today, we're going to talk about the context and the need for greenhouse gas emissions reduction, the challenges associated with taking steps to reduce greenhouse gas emissions, what opportunities should be considered, and some example greenhouse gas emissions reduction options that we've looked at. Then we'll go on to talk about our approach and tools to show how we identify and evaluate options and develop a roadmap for asset decarbonisation. And then some option examples to illustrate the approach. So the North Sea Transition Deal is the industry commitment to reducing greenhouse gas emissions in order to play its role in helping the UK meet its net zero commitments. The industry is committed to reducing greenhouse gas emissions by these percentages over the next decade compared to 2018 baseline, which is around 19 million tonnes of CO2 equivalent. And as the North Sea Transition Deal says, this is going to need to be a decade for change. So the OGA Stewardship Expectation 11 provides guidelines and expectations on operators for all stages of the developments, managing and reducing carbon emissions. It challenges the industry to go further and faster than the North Sea Transition Deal, or risk losing its social licence to operate. And for producing platforms, it states that you should have a greenhouse gas emissions reduction action plan and a greenhouse gas emissions reduction project hopper. Now this graph shows the magnitude of the CO2 emissions per platform based on 2020 figures. There's lots of platforms in the range of 100,000 to 300,000 tonnes of CO2 equivalent per year. Some as high as 500,000 to 600,000 per year. This slide shows a typical breakdown of emissions on a platform. So on average, around 70% of the greenhouse gas emissions come from generating power. So that's either main platform power or direct drives, gas turbines. The other 30% is mostly flaring, so broken down into routine flaring and emergency flaring. And in the next three slides, we'll consider the challenges, opportunities, and the options to reduce greenhouse gas emissions from power generation, from flaring, and then taking into account the fact that we're dealing with ageing offshore infrastructure. So for power generation, we understand you have to generate power on a platform. Power is required to provide the motive force to get the products, the gas and or the oil from the platforms to shore. For enhanced oil recovery, things like gas lift, and for reservoir management, so gas injection and water injection. It's also used for other utilities and for baseload power for the facility. Now, gas is normally the primary fuel, diesel as a backup. Another thing to consider is that power generation typically generates heat in waste heat recovery units, so you need to consider how you're going to provide that heat if you're looking to provide power from another source. So in terms of opportunities, obviously for power, we need to try and look at ways of reducing any of the power demands on the platform, increasing efficiency of equipment or the power generation itself. We could provide an alternative fuel or power supply, even replacing diesel with a lower emission fuel, or a different source of power, such as electricity. And then if you use less gas in your turbines, you'll have more to export and sell, so potentially higher revenue from the facility. And that also may avoid the need for import gas once the facility becomes gas efficient. Now, what options should we be looking at? Well, these are some examples. We're not saying this is all of the options, but it gives a flavour of the types of things you should be looking at. We'd want to look at optimising the plant as far as possible, so reducing any pressure losses and blockages, ensuring equipment is operating as efficiently as possible. Right-sizing equipment, so rewheeling, restaging, or even replacing rotating equipment to avoid recycling and operating to a more efficient point. And then electrification, so replacing the fuel gas with energy from electricity from a green source. So flaring, again, we understand that sending some gas to flare systems is necessary for offshore operations. You'll have continuous flaring from low pressure sources. And even last stages of separation can be sent direct to flare. Each time you start up and shut down will require some flaring. And as gas is treated to flare at low pressure, it is hard to recover. What opportunities might there be? Well, can you look for ways of reducing routine flaring? Can you improve your startup procedures and look for production efficiency improvements to reduce trips and reduce emissions? And then can you recover flare gas? Taking account of the fact that you need a suitable place to recover that gas to. So in terms of options, one continuous flare source on a platform is stripping gas, the TEG regen. So can you look to optimise that? Put a focus on production efficiency, so reducing the number of trips that cause flaring events, and then ultimately look at flare gas recovery to recover all the gas that's routed to the flare system routinely. So there's a number of challenges with the fact that assets are aging and you're in an offshore environment. Assets tend to be less reliable, with lower production efficiency. Equipment such as pumps and compressors may be oversized. And through field life, assets may become gas deficient and have to import gas to meet the shortfall in gas required for fuel gas. Space and weight considerations may add cost to any proposed modifications, and the distance from shore makes connections to grid infrastructure challenging. So overall then, the remaining field life may be too short to make any significant investment in greenhouse gas emissions reduction projects viable. In terms of opportunities, as your production declines, there may be less power demand anyway. So if you can estimate future power demand, you can demonstrate that the emissions from power generation will reduce over time. And we do find that there are synergies between emissions reduction opportunities and the OPEX reduction opportunities, which might improve the viability of some projects. And then offshore, in fact, in an offshore location may mean that you're well placed to take advantage of nearby infrastructure, such as offshore wind. In terms of options, systems such as gas lift and water injection should be continually optimised to reduce emissions so that you're not over-injecting and wasting energy. Can you reconfigure parts of the plant to both reduce OPEX and reduce emissions at the same time? Worth considering whole-scale field redevelopment, so tying production back elsewhere and converting platforms into wellhead platforms, and then making connections for electrical infrastructure from nearby wind farm developments, etc. Now I'll hand over to Carinne, who's going to take you through our approach to asset decarbonisation.
Yeah, thanks, Peter. So to address the challenges presented by Peter, we have defined a structured approach divided into 4 steps. So the first step is to define the baseline and quantify the emissions for the current configuration, identify the emission sources and the key contributors. So we can do that for the full life of field profile to predict or define the emissions for the current configuration. And the second step is identifying the emission reduction opportunities, EROs. Is typically done during a brainstorm workshop, and we're working with a preset list of opportunities, and we're just reviewing if they can apply to the particular asset. And at the end of the workshop, we've got an EROs hopper that we will present to the client. And then we assess each of the opportunities. The core of our assessment is using the Kent carbon intensity reduction tool. What it does, it makes an automatic link to the process simulator and automatize the CO2 emission calculations. We perform a technical feasibility assessment. We review technical constraints, technical risk, and brownfield modification required. And we also perform a preliminary technical economic evaluation to review or be able to compare the options together. So all of these individual opportunities are then reviewed to see if they can be combined or if there are synergies between them. We also review schedule and timelines because some of the opportunities won't be able to be implemented in the short term. And that allows us to define a fit for purpose action plan with a robust demonstration that the targets can be met. So the core of our assessment is using the carbon intensity reduction tool. It makes an automatic link to the process simulator Unisim or ICIS using another application called MESCAP that we have developed. We input all of the opportunities identified and a number of financial assumptions such as carbon credit cost, oil and gas sales price, and the KPIs that we want to use for ranking the options. And we input as well a number of life of field data, such as the production profiles. And because the calculation is performed automatically, we can review a number of production scenarios or sensitivities. We input as well equipment reliability and other data, such as the thermal efficiency for the power generators. And the software provides us a number of outputs. The key one is the CO2 quantification, so how much benefit we will get for each of the options, and also economic parameters such as NPV. And the NPV includes impact to the oil and gas revenue, how much carbon credit costs we have to pay, operational costs, and required upfront capex. And once we've got all of these results, we review or we rank the options using the criteria input into the software. And this allows us to review the best options. And all the best options are then combined into a roadmap. And this will be a roadmap that is fit for purpose for the asset. So I'll show you a number of examples of results from the tool. So this is a bar chart that shows the benefits. So the bar is the reduction in CO2 for each of the options. So the bigger the bar, the bigger the benefits. So we can see on the example that full electrification provides the largest reduction in CO2. And the orange line is the cumulative NPV over life of field. So again, if we look at full electrification, we can see that the NPV is quite low compared to the other options. And this is due to the large capex required upfront. So we can also plot the results in a cost-benefit axis. So where we want to be is in the light blue corner, so high benefits and low cost. In reality, the options will probably be in the dark blue corner with some benefits and requiring minimum or some cost. And to get larger benefits, we will probably require a large amount of capex. And the options that will be in the top left corner, so with low benefits and high cost, will be discarded. I'll give you a number of case study examples. So the first set of examples are on reduction of CO2 from the exhaust from the power gen and the drivers. So the first example is rewheeling a mole pump. The mole pumps are sometimes sized for a high throughput in oil. So in our example, 100 MBD, where the current throughput is much lower. So in our example, 15 MBD. So the pump has to operate on recycle, which is not efficient. So by resizing the mole pump, we can reduce the CO2 from 1.6 to 0.4 kiloton per year. So for about 2 million pound capex, we can save about 0.1 million pound per year in CO2. And it's just the benefits associated to the carbon costs, not accounted for benefits such as reduced maintenance on smaller pumps or having less trips to restart a smaller pump as well. So the second example is on partial electrification. So it's replacing the power generator by an external power supply. So in our example, we've got a 10 megawatt power generator. So we can manage to reduce CO2 by 205 to 67 kiloton per year, so quite a large amount of savings in CO2. But it requires quite a large capex, so 20 to 50 million pounds estimated here. for a benefit that will be equivalent to 9 million pounds per year. So we can get quite a high benefit in CO2, but it comes with quite a great capex upfront. And the cost here is just the capex associated to brownfield modification on the asset, and not accounted for cost to supply the power to the platform. So the second set of examples are reducing CO2 from the flare. So one of the continuous flaring in operation can be the stripping gas from the glycol regeneration system. So if we reduce it from 1 million scuff to 0.5 million scuff, we can save about 9 kilotons per year in CO2. So that is just an optimization. So with no capex required, we can save 0.6 million pounds per year in CO2. And that is ensuring as well that the dew point in the gas is met. And the next example is a brownfield modification, so flare gas recovery to recover the continuous flaring during operation. So if we recover 1 million scuff of gas, that is equivalent to about 16 kilotons per year of CO2. So for about 5 million pounds of capex, we can save per year about 1 million pounds just in CO2 savings. So all of these individual opportunities are then combined to form a roadmap. And this is a graph that helps to ensure that the targets are met. So to achieve a target of 10% reduction in 2025, we need to combine option 1 and 2, so the blue and the yellow. And this may be operational changes or changes to the set points of the trips to reduce the number of trips. And to achieve a further reduction in CO2, 25% in 2027, we need some brownfield modification. So we need to combine on top of that option 3, 4, 5, and 6. And this may, for example, consist in rewheeling a compressor to make it more efficient. And to achieve a further reduction, 50% in 2030, we need option 7, which provides quite a large amount of benefits. And in this example, the brown bar is the partial electrification. So I hand over now to Peter for the conclusion.
Yeah, thank you, Carinne. So we've shown in the presentation here some of the challenges inherent in reducing greenhouse gas emissions offshore. Platforms need power for a variety of purposes, not least getting the oil and gas onshore. In most cases, that comes with greenhouse gas emissions. Putting gas to flare systems is required for a number of operations, such as pressure control, startup and shutdown. And the age of maturity of offshore facilities means that rotating equipment may be oversized and therefore inefficient, increasing the power demand. We've seen some examples where on their own, projects to reduce greenhouse gas emissions may not be economically viable. So you need to consider other benefits in terms of reduced OPEX or improved availability in order to make them worthwhile. And however, also we've seen that there may be opportunities to reduce current emissions without any investment. So therefore, with a method to estimate greenhouse gas emissions over field life, which is linked to production profiles, together with a systematic approach for identifying, evaluating and selecting options, emissions reduction roadmaps and action plans can quickly be developed so that within facility constraints, you can clearly demonstrate what can and can't be done in order to meet greenhouse gas emissions reduction targets. Thank you very much for listening, and we can take any questions now. Thank you.